You just completed a little activity where you were bringing a magnet nearby, sorry, bringing a compass nearby a magnet, seeing which way the compass pointed. I want to draw, hopefully, the results that you would have gotten. We put a compass at each of these stars. If we put it right here, it's going to point somewhere around here, and so on. Yours might not look exactly like this, but hopefully it's kind of like this at least. How many people got something for the first diagram that looks something like this? Something? It's not going to be exact, right? If it looks something like this, that's good, because that's what it's supposed to look like. Now I want to join some dots like we did back in kindergarten. If we start joining these ones, and we start joining these ones, and then we start getting a magnetic field pattern that surrounds this bar magnet with a north pole and a south pole. The magnetic fields point in the direction of your little arrows, meaning that the magnetic field points in the direction that the compass points. Now, you're not going to recognize this on one level, but maybe on another level you might. I'm going to try drawing a couple of charges. Remember that what I'm about to draw is different than what I just drew. Okay, what I just drew are magnetic fields. I'm going to draw the fields surrounding charges, which are electric fields. But I want you to see the pattern here. If you draw the electric field surrounding these charges, it's going to look something like this, right? It goes away from positive toward the negative. We just wrote a test on this. Okay, you guys know this. You guys recognize this? The electric field that surrounds these charges? It looks an awful lot like the magnetic field surrounding this magnet, right? A north pole and a south pole are not positive and negative charges, but the field surrounding them is very much like the field surrounding a positive and a negative charge. Take a look at the next diagram that you guys drew. All kinds of dots on this one. Dots should look something like this. Okay, not necessarily exactly, but start joining some dots here. What's it going to look like? Well, if I join these together, and then these, and then these, and then I start doing this, and I start doing this, what does that look like? Well, it's a magnetic field surrounding two bar magnets with a north pole against a south pole. Take a step back from this for a second, and it should look a little bit familiar to you. If we were to draw two charges, a negative and a positive here, the electric field surrounding those two charges would look something like this. Kind of like between the north and the south there. If I was to draw another charge over here, a positive, and another charge over here, a negative, then the field would look something like this. Which, again, looks an awful lot like the magnetic field surrounding these two bar magnets. It's not the same thing, but it looks a lot like it. And what about our last configuration of magnets here? Here we had a north against a north. We should have had little arrows at our various points looking something like this. We connect those dots like we did back in kindergarten. Going to look something like this. What does that remind us of? Well, if we drew two positives right here, positive and a positive, the field line in between those two positives is going to look like this. That is the electric field. Okay, it looks a lot like the magnetic field between north and north. If we put another negative charge over here, another negative charge over here, then the field lines should look something like this, where once again, the electric field shape and direction looks an awful lot like the magnetic field shape and direction given this configuration. It's not the same thing, but you can see that there's going to be a lot of similarities between electricity and magnetism, just like there was a lot of similarities between electricity and gravity. Not the same thing, but a lot of similarities. Since we've drawn these diagrams and done this little activity, I want to define now the direction of the field. We define direction of a gravitational field and an electric field. So let's define the direction of a magnetic field. If you remember, the gravitational field direction was defined as the way that a mass moved when placed in the field. You place a mass in a gravitational field, the mass will move in the direction of the field. We could also define gravity field as the direction as being toward the producer, okay? Toward the producer. So it's either the way that a mass moves when placed in the field, or it's toward the producer. An electric field we can define as the way that a positive charge moves when placed in the field, or it's away from positive and toward negative. We have a similar way for defining the direction of the magnetic field. It's the way, listen, we kind of already led you into this already with the activity that you did. It's the way that a compass needle points when placed in the field. It's not the way that a mass moves when placed in the field. It's not the way that a positive charge moves when placed in the field. It's the way that a compass needle moves when placed in the field. Well, there's another way we define it as well. That other way is related to the second way we define gravity field and electric field. But it's not toward the producer, like it is for gravity. It's not away from positive toward negative, like it is for electric fields. Rather, it's away from the North Pole and toward the south, from north to south. You guys have all finished writing these notes, but nobody asked me the question that I was hoping somebody would ask me. Sometimes when we write notes, we just write them. We blindly write them. And you know what? That's worth something. Blindly writing notes teaches you something. You've got to internalize something as you're writing notes. But if we can actively think about what we're writing, so much the better. If we actively think about what you just wrote down, you may have a question. There seems to be a bit of a conflict here. The direction that a compass needle points when placed in the field. That's the first way we define the direction of a magnetic field. The second way is from north to south. If we look at those two definitions of direction of a magnetic field, it seems to be telling us that the magnetic field is pointing which way? Toward the south. Compasses point in the direction of that field. The magnetic field points toward the south. Compasses point toward the south. But wait a second, they don't. If you're ever lost in the woods and you're looking at a compass, you know that the compass needle is pointing towards the north, right? But it isn't. It isn't pointing toward the north. When you look at a compass needle, that red tip of the compass, what you're really doing is looking at the north end of the compass. It's not pointing north. It's pointing south. Now, I know that's confusing right now, but we'll talk about it just for a couple more minutes to hopefully alleviate that confusion. Geographically, way up there, way up past Calgary, way up past Alberta in the Arctic, geographically that's north. Magnetically, it's not. Magnetically, it's south. Where the penguins live, down in Antarctica, geographically that's south, but magnetically it's not. Magnetically, that's north. Now, when we're navigating, we don't think of it that way, right? When we're navigating, we say, oh, let's go 100 kilometers to the north. When you're in your car, and the compass in your car says, when you're driving to Edmonton, you're going to the north, okay? It's fine. It says to the north. We're going to the north, right? No, we're not going to the north. We're going to the south. Here's the reality. The convention is that's north. But it just isn't. It's south, magnetically. But it doesn't really matter as long as we're all calling it the same thing. Okay? As long as we're all wrong about which way we're calling it, then it doesn't really matter if it's wrong. Okay? That's magnetic south. Well, we call it north usually when we're navigating. We could call it pumpkin pie. As long as we all call it the same thing, it doesn't really matter. Does that make sense? I'm about to rock your world here. Okay, I'm about to change everything you've ever believed in. There's a picture of the Earth. The Earth has a magnetic field surrounding it, much like a bar magnet has a magnetic field surrounding it. Now, there's not a bar magnet inside the Earth, but the shape of the magnetic field surrounding the Earth is like that would surround a bar magnet. We don't really know for sure entirely what causes the magnetic field surrounding the Earth. We think it has to do with the churning magma deep within the Earth, and maybe there's charges, electric charges that are in that moving magma, and those moving charges generate a magnetic field. And we think it's something like that, but we're not entirely sure about what causes the Earth's magnetic field. Bottom line is, there is a magnetic field surrounding the Earth, and its shape is much like that surrounding a bar magnet. This is the direction of that magnetic field. It goes from the bottom, where Antarctica is, to the top, where northern Canada is, right, the Arctic. You can see that the field lines point in that direction, which means that the polarity of that will draw it as a bar magnet inside the Earth. The polarity of the Earth's magnetic field has got to be north on the bottom and south on the top. It has to be, by definition of the way we define direction of magnetic field. So, what does that tell us? Well, it tells us, if you guys are little kids and you're looking for Santa Claus, the reason you didn't find him is because you're looking in the wrong place. You should have been looking in the South Pole, not the North Pole. Santa Claus doesn't live in the North Pole. He lives in the South Pole. Somewhere down south in Antarctica, the penguins have got this massive warehouse of letters to Santa Claus because kids are sending their letters to Santa Claus, North Pole, H-O-H-O-H-O, and they arrive down in Antarctica, and they just sit on them for the last 15 years or so. Maybe that's why you didn't get what you wanted when you were 8 years old for Christmas, because the penguins are just laughing at your letter, throwing it in the warehouse. This doesn't need to change anything, really. Okay? If you're ever lost in the woods, and somebody says, oh, I got a compass, let's find our way out. Don't say, oh, my physics 30 teacher told me that everything's reversed, so you're going to navigate saying that's north, right? It just isn't magnetically north. It's geographically north. It's magnetically south. Get it? All right, you don't need to write down what you see next. In fact, that's it for writing things down here. I just want to put this up for perspective here. This table that comes from your textbook that shows the strength of various magnetic fields. The symbol for magnetic field, by the way, is B. It's a vector field, so it has a little half arrow over it. The units for magnetic field are capital T. Tesla, it stands for. The strength of the Earth's magnetic field, guys, you don't have to copy this down. Okay, you don't have to memorize any of these numbers. The strength of the Earth's magnetic field is, it varies depending upon where you are on the Earth. And you know what? It varies with time as well. 100 years ago, the Earth's magnetic field was about 10% stronger than it is now. It's actually weakening over time, quite dramatically, actually. Within my lifetime, it's weakened quite dramatically by several percent. But on average, it's about 5 times 10 to the minus 5 Tesla. That's a pretty weak magnetic field, really, right? 10 to the minus 5 Tesla. By the way, it's weakening by about 10% in the last 100 years or so. There's some thought out there by scientists that we may be actually of a reversal. The Earth's magnetic field may be in the process of reversing itself. It happens about every 250,000 years throughout history. We have strong geological evidence to support the fact that, to support the concept that the magnetic field surrounding the Earth reverses about every 250,000 years. And the last time it happened was about 750,000 years ago. So we're about 500,000 years overdue, according to historical geological records. We don't know if that's what's happening. The strength of the Earth's magnetic field is decreasing. But we don't know if it's some other reason why it's decreasing or we are in the process of reversing. If it does reverse, we don't know if it's going to happen overnight or whether it's going to take 200 or 300 years for it to reverse itself. Don't know. Lots of unknowns here. But we may be literally in a period of transition where perhaps even your kids or grandchildren may have the magnetic field going the other way around. So where we say Santa Claus lives in the South Pole now, technically, well, Santa Claus may actually, in a couple generations, live in the North Pole. We don't know. Okay, it's possible that's happening. We don't really know. Oh, what would happen if it happened overnight? Well, first of all, the most important thing is the letters would all go to the right place. Santa's letters would go to the right place. Okay. Less importantly, okay, birds would get all messed up. Okay, they want to fly south for the wintertime, right? But they have this little magnetic compass in their heads that guides them in the right direction. So birds would get all messed up. What else would happen? Well, if it actually weakened to the point where the magnetic field strength was 0 or close to 0 in between the reversal, we have an issue with solar wind and charged particles coming from space that were normally shielded from would penetrate the Earth's atmosphere and come into the Earth and cause all kinds of issues with satellite communications and with even with health issues. The Earth's magnetic field protects us quite well from these charged particles coming from space. Some of them make it through, okay, most of them don't. Partly because of the Earth's magnetic field, partly because of the Earth's atmosphere, just absorbing some of them. But more of those particles would get through. And that would create health issues. These charged particles can cause cancers and whatever. That's not to suggest that there would be this epidemic of cancers, but there would probably be increased incidences of things like that, yeah. But can't worry about it, right? Because, in the end, it could be another 200,000 years before it happens. Or it could be another 200 before it happens. The typical strength of a bar magnet, it varies, right? It varies. But on average, it's about 10 to the minus 2 Tesla, which means a typical bar magnet is about 1,000 times the strength of the Earth's magnetic field. We don't think of that, right? We think, oh, the Earth's magnetic field's got to be stronger than a bar magnet. The Earth is way bigger. But when you guys just did the activity that you did 20 minutes ago, half an hour ago, you put the compass near a bar magnet, and all of a sudden the compass was deflected. The compass was deflected far more by the bar magnet than it was the Earth's magnetic field, right? The compass should point that way, but it didn't when you put it near a bar magnet. The bar magnet had a strength that was, the ones we used were weak, but they were still way stronger than the Earth's magnetic field, right? On average, they're 1,000 times stronger. A sunspot, which is kind of like weather on the sun, releasing these charged particles. 10 to the minus 1 Tesla, about 10,000 times stronger than the Earth's magnetic field. You ever find yourself out for a Sunday afternoon drive? And in space, that is. And you happen to be getting close to the sun? That compass that you're holding in your hand to navigate is going to start going wonky because the sun's the magnetic field caused by these sunspots is really, really strong, way stronger, 10,000 times stronger than the Earth's magnetic field. How many people have ever had an MRI for one thing or another? Just a couple of you? Okay. When you get an MRI, they ask you all these questions, right? There's a survey that they ask you. Lots of it's about metal. You ever had metal in your eye? Or who cares? Who cares? You should care if you get an MRI, because in the end, if that metal that was in your eye was ferromagnetic, and you're exposed to a magnetic field strength of about 15 Tesla, then that might create some issues. This is 10 to the 1, right? 10 to the positive 1. So that's what, 1,000,000 times stronger than the Earth's magnetic field? 1,000,000 times stronger. To give you some perspective on this one, the strongest human-made magnet ever made, 40 Tesla. Same order of magnitude, about twice the strength of an MRI machine. So those are strong, right? Strong magnets, really strong magnets. Here's what you want to stay away from, though. The magnetic neutron star. It has a magnetic field strength of 10 to the 11 Tesla. That's so strong, I don't even know what the effect would be. But likely, that's so strong that if you got close enough to it, you're out for that Sunday afternoon drive and you're approaching a magnetic neutron star, you would probably actually go brain dead because you wouldn't have any oxygen to the brain because all the iron would be sucked out of your blood by this magnetic neutron star. That's how bad it would be. That's how strong this is. Hey, here's the good news. There's lots of other things that would kill you long before you ever got to a magnetic neutron star that you're not going to ever have to worry about that taking place. Okay? So, in synopsis here, guys, last thing we do today, just a little table that summarizes our three types of fields that we've learned about. Gravitational fields from last year, electric and magnetic fields from this year. What's the cause of them? What's the source of these fields? Well, gravitational field is mass. Right? An electric field is charge. A magnetic field is, I don't know why I don't change this. One of these days I got to change this. The source of a magnetic field is a ferromagnetic material with aligned domains. What's a better way to say that? Although it doesn't sound nearly as intelligent. What's a better way to say a ferromagnetic material with aligned domains? It's a one-word answer. A magnet. I almost poked you with that. A magnet. Okay, the source of a magnetic field is a magnet. The direction, well, of course, gravity is always attractive. Electric field can be attractive or repulsive. And the magnetic field can be attractive or repulsive as well. So similarities between all three of these fields, but differences between all three of these fields as well.